AND gate. When I complement it, I am going to get NAND gate. Again I am going to complement that NAND gate. At last it will going to give me the AND gate. We can create AND gate, OR gate and NOT gate by making use of this NAND and NOR gate, so that it will be considered as what? Universal gates. Based on the De Morgan's law, x dot y whole bar is also equal to what? X bar plus y bar. Hello everyone, welcome back to the last session on chapter 3, that is Logic Gate. I am Rohini TS, lecturer, Department of Computer Science, Vidhyaashram Pre-University College, Mysuru. So in my last session, we learnt about derived gates. So what is derived gates then? So derived gates are the gates that are designed or implemented by making use of the basic gates. So that was the definition of a derived gates. So and we also know that we have several basic gates. So which are the basic gates? So the basic gates includes NOT gate, OR gate and AND gate. So by making use of these basic gates, we are going to create a derived gates. Then which are the derived gates that I have discussed? First one is NAND gate. So NAND in the sense what? It is a complement of the AND gate. So it will going to take two input and it will going to complement. So if it is x and y, then it will become x dot y whole bar. So this is about NAND gate. Then what about NOR gate? So NOR gate is nothing but it is a complement of the OR gate. Then how we are going to write it? So it is also contains two or more input, and when it comes to the NOR, OR is added with inverter so that it becomes x plus y whole bar. This is about NOR gate. Then I have discussed about XOR gate. Right? XOR in the sense what? Exclusively OR gate. It is a different form of the OR gate. Then how we are going to represent? So it may take two or more input. Along with that, it has a curved line. So this represents the XOR gate. So then what will be the output? How we are going to represent this XOR gate? That is plus surrounded by circle Y. So this is about XOR. Then we have a last type, that is XNOR. So when it comes to the XNOR, this is exclusively NOR gate. So then how we are going to represent? So it is same like a XOR, but that will be added with a inverter. If it is added with an inverter, then we are going to call that as XNOR. So here X and Y are the two inputs and exclusively OR gate with inverter. So it becomes XNOR. Then how to represent it? X dot, that is surrounded by circle, then Y. This is how the representation of the derived gates will going to happen. So in today's session, we are going to see what is universal gate. So we are going to consider NAND and NOR gate as the universal gate. Then we are going to learn about realization of all the basic gates using a NAND gate. Very, very important question for 3 mark. Important question for 3 mark. Here you can expect either realization of a basic gate using NAND gate or by making use of this NOR gate. So when it comes to the universal gate, so we know what is gate, what is basic gate and what is derived gates. So when it comes to the universal gate, we are going to consider NAND and NOR as a universal gate. So why we are going to consider NAND and NOR as a universal gate? By making use of this NAND and NOR gate, we are going to create or we can going to implement all the basic gates. So that is, we can create AND gate, OR gate and NOT gate by making use of this NAND and NOR gate, so that it will be considered as what? Universal gates. So here, what is universal gate then? It is a gate which all the basic gates can be designed. So we know what is basic gate. By making use of this universal gate, we are going to implement or we are going to create a basic gate so that it will be considered as what? Universal gate. So here NAND and NOR will be considered as what? Universal gate. So by making use of NAND and NOR, I can create AND, OR and NOT gate. That is what about this realization of all the basic gates either using NAND gate or either using NOR gate. So before getting into today's session, you have to understand two things, that is De Morgan's law. So when it comes to the De Morgan's law, this is a basic law of a Boolean algebra. So De Morgan's law, it has two laws. So there we have two De Morgan's law. When it comes to the first law, here x dot y whole bar is equal to x bar plus y bar. So what is this? Nand gate. So x dot y are the inputs and we have a product. When it comes to the product, it will be AND gate. But it has a bar that is complemented. So it will be NAND gate, that is also equal to what? Complement of the x input and complement of the y input, and we have to sum it up. So this is about the De Morgan's first law, that is De Morgan's first law. Next we have a second law, that is x plus y whole bar, that is equal to x bar into y bar. So this is De Morgan's second law. De Morgan second law. Here when it comes to x plus y whole bar, that is nothing but what? NOR gate. That is also equal to complement of x product and complement of y. So you just need to understand these things in order to make a realization of all the basic gates by making use of the universal gate. So now we'll see how can I convert a NAND gate to any of the basic gates. So which are the basic gates? AND, OR and NOT we have. So when it comes to the first one, here I am converting from NAND to NOT. So understand one thing, NAND in the sense how we are going to represent. So this is NAND gate. What must be my output? That is NOT gate. How many input and how many output NOT gate will going to happen? So it will going to take only one input and it will going to produce only one output. If, for example, if my input is x, then the output will be x complement. So this is what you have to understand. When it comes to this NAND gate, x and y, here x dot y whole bar. So this is what? The basic thing that you have to understand. Now we'll see how I am going to convert this NAND gate into this NOT gate. So here you can see the image or you can see the logic diagram of conversion of the NAND gate to NOT gate. So we know that in order to get the NOT gate, we must give only one input and it will going to give only one output. So here, when it comes to the NAND gate, how many input it will going to take? It will going to accept either 2 or more. So in this case, x and y are the two inputs. So when I complement it along with the product, it will going to give us x dot y whole bar. Just understand right now. Here, what I am doing? Purposely, I am going to shortening the input. Two inputs to a single input. Why? Because in order to make it as NOT gate, we know that it will going to accept only one input and it will going to produce only one output. So that instead of taking two input as x and y, I am going to shortening and I am going to consider a single input. But you have to understand it has two input, but purposely we are going to shortening it. So this represent two input. So what I am doing? I am shortening the two input into single unit, that is x. Then that will be fed into this NAND gate. So we have an inverter, it is a NAND gate. Then what will be the output? For example, here x and y are the input, the output will be x dot y whole bar. But here I am taking two input, that is x and x. Then what will be the output? It must be x dot x whole bar. Why? Because my both the inputs are x and x. So the output must be x dot x whole bar. So that you can see here, when it comes to the NAND gate, f is a variable that will going to hold the value of this input, x dot x whole bar. So that represents what? Input, and when it complemented with a NAND gate, it will going to give us x dot x whole bar. Okay, and we have one rule, that is x dot x whole bar, that is equal to x bar. How it is equal to x bar? For example, 1 dot 1. 1 into 1 will be what? 1. And 0 dot 0. What will be the output? 0 itself. So that here x dot x whole bar, that is also equal to x bar. So that is complement of the input. So what was my input? That is x. But now, as of now, the output is x bar. So that we got a NOT gate. The input was x and the output is x bar. So that it will going to realize that NAND to NOT. So now we'll see how can I derive it in a logic form. Here, I'm seeking for a NOT x. Right? That means what? I have an input and I need to give that NAND gate as an input and it has to give me the output of NOT gate. So here NOT x is equal to, how I am going to write the NAND gate? So we have two input. Which are the two input? X and x. So that x, which operation I am performing? NAND, and I have one more input called x. So here x NAND x. So x NAND x. How to represent the NAND? That is a product, right? And NAND in the sense it has a complement. So that it will become x dot x whole bar. It become what? X dot x whole bar. So here I have discussed that when it comes to the De Morgan's first law here, what it indicates, x dot y whole bar, that is also equal to x bar plus y bar. So can I take this De Morgan first law in order to solve it? Yes, we can take. How I am going to do that? Instead of x and y, here I am taking x and x. So when it comes to the x and x, instead of this x bar plus y bar, I can take x bar plus x bar. Because my both inputs are x itself, because I have shortened into a single input. So here x dot x whole bar, that is also equal to x bar plus x bar. Here either it can be product or sum, then that will be equal to the same input. That means x bar plus x bar is also equal to x bar. That is 1 plus 1 is equal to 1 or 0 plus 0 is equal to 0. Okay. So based on that law, we are going to consider this as x bar plus x bar as x bar itself. So my input was x and now I got the output x bar. So that is the inverted input will going to give us the NOT gate. So this is how, based on the De Morgan's law along with some of the basic postulate, we are going to convert a universal gate into basic gate. So this is how we are going to convert NAND to NOT. So now we'll see how can I convert NAND to AND. Here NAND to AND. So we know what is NAND and what is AND. So when it comes to the NAND, x and y are the two inputs and it will going to give us x dot y whole bar. So but I am converting this NAND to AND. So when it comes to the AND gate, what must be the output? So here it will going to take two inputs and it will going to give the output x dot y. So this is the result that what I require. So from NAND to AND. So now we'll see here x and y are the two inputs. So which gate it is? It is NAND gate. How can I consider this as an AND gate? Because it is a complemented version of the AND gate. Here we have a inverter. So that here NAND gate 1. So what it will be the output? The output will be F1 is equal to x dot y whole bar. Why? Because x and y are the two inputs. I am using NAND gate so that when it complemented, it will going to give us a product with a complement, that is inverter, x dot y whole bar. After this, I am going to feed this input into another NAND gate. So here I am taking two NAND gate in order to get a AND gate. So understand one thing, AND gate. When I complement it, I am going to get NAND gate. Again, I am going to complement that NAND gate. At last, it will going to give me the AND gate. So that is what you have to understand. So x dot y whole bar is an AND gate 1 and I am going to convert it x dot y. I need to convert this into x dot y. That means I am supposed to convert from NAND to AND. So now we'll see here x dot y whole bar is the output of NAND gate 1. So I am going to feed this x dot y whole bar to the another NAND gate. So here what I am doing, I am shortening the two input into a single input signal. So that understand now, x dot y whole bar is an input, but when I am shortening this one, you have to understand both the inputs are same. So that what are the both inputs? That is x dot y whole bar and x dot y whole bar. So these two are the inputs that I am giving to this one. So if I am giving, so we know what is NAND gate, x dot y whole bar. Here x represent this x dot y whole bar, x dot y whole bar, and this y represent another one, that is x dot y whole bar. So we know NAND gate, that is complete or a fully barred. So here we'll see F2 is equal to x dot y whole bar. So why? Because here x dot y whole bar is a one input. So when it is shortening, we get to know that both the inputs are same. So when both the inputs are same, here x dot y whole bar is nothing but NAND gate, and x is equal to 1 x dot y whole bar and y is equal to another x dot y whole bar. So how can I take that as an input? X dot y whole bar into x dot y whole bar, that is y value, and whole complemented. So when it comes here, this bar get cancel, here this bar get cancel. So only we are end up with x dot y into x dot y. So based on this rule, we are going to have only x dot y. So this will be the output. So if it is x dot y, we all know that is nothing but AND gate. So here input is x dot y whole bar, x dot y whole bar. So this is NAND gate 2. So when we are feeding this x dot y whole bar and x dot y whole bar as an input to the NAND gate 2, then it will be converted into x dot y whole bar based on double bar. X dot y is an input. I am using NAND gate so that it will be complemented. So this bar will get cancelled. So I will end up with this x dot y. This is how the conversion of NAND gate to AND gate will going to happen. Here you can see that x NAND y, that is x dot y whole bar. So we know that based on the De Morgan's law, x dot y whole bar is also equal to what? X bar plus y bar. So after that we will get to know that this x NAND y is nothing but what? X bar plus y bar. So now I have two inputs, so that x NAND y, this is one input, and NAND, and we have one more input, that is y, so that x NAND y. So what x NAND y represent? That represent x bar plus y bar, and we have a NAND gate, and here I have x NAND y. X NAND y represent what? X bar plus y bar. Okay, so these two are the inputs. So I am using NAND gate. How I am going to write the NAND gate? That is x bar plus y bar dot. So dot represent the NAND gate along with a whole bar, so that it will be whole barred. So here we have a two input, that is x plus y whole bar. Why? Because x dot y whole bar, that is also equal to x bar plus y bar. So we are using the De Morgan's law. So x bar plus y bar NAND x bar plus y bar. How can I write this? X bar plus y bar dot in the sense NAND, and I have one more input x bar plus y bar, that will be whole complemented, that represents the NAND gate. Let me write here x plus y whole bar into x bar plus y bar, and that will be whole complemented because we are using NAND gate. So if you look here, x bar plus y bar, that is also equal to what? X dot y whole bar. Why it is also equal? Based on the De Morgan's second law. So here instead of x bar plus y bar, I am going to take it as x dot y whole bar, and same thing for the next input. So here we have a whole complement, that when it comes to the NAND we have a whole complement. So let's get it cancelled. So bar will get cancelled. So we are end up with x dot y into x dot y. X dot y into x dot y. For example, if my input is 1, 1 dot 1, what will be the output? 1. If my input is 0 dot 0, the output will be 0. So that means what? X dot y into x dot y, that is similar to x dot y itself. So now we got the output of this AND gate. So this is how we are going to convert NAND to AND. So we are supposed to take the two inputs, that is 2 NAND gate, 1 NAND gate, xy. So we are going to get the value x dot y whole bar. Here I am going to shortening the two input, x dot y whole bar, x dot y whole bar. Based on the De Morgan's theorem, x dot y whole bar is also equal to x bar plus y bar. So after that, I am going to recomplement it, then bar will get cancelled. X dot y whole bar, that is also equal to x dot y. So we will going to have a AND gate by the NAND gate. So this is NAND gate 1, NAND gate 2. So the output will be x dot y. So now we'll see how to convert this NAND to OR. So we know the output of OR gate, right? What must be the output of OR gate? We are supposed to get x plus y. This will be the output, but the input is x and y, but we are taking NAND gate. So what is the NAND gate output? That is x dot y whole bar, that needs to be converted into x plus y. So then how we are going to convert from the NAND to OR? We'll see now. I have two NAND gate here. How many NAND gates I am taking? 2 NAND gate. So what I am doing here, I am shortening the input value. That means what? I am taking x as a input and y as another input. So when I am shortening that, you have to understand that both the inputs are same, that is x and x. So when it comes to the NAND gate 1, x and x are the two inputs. So the output will be what? X dot x whole bar. So this is regarding NAND gate 1. So I have NAND gate 2, that is 2y are my input. So that the output will be y dot y whole bar. Y dot y whole bar. So now what you have to understand? X dot x whole bar is one input and y dot y whole bar is another input. So that I am going to feed to another NAND gate. So we'll see here, when it comes to the NAND gate 1, x dot x, then the output will be x dot x whole bar. When it comes to the second NAND gate, here I am giving the y as an input, so that when it is shortening, both the inputs are same, so that NAND gate is x dot y whole bar, but my inputs are y and y, so it will become y and y whole bar. So these two are the inputs that I am going to feed to the another NAND gate. So how I am going to write? X dot x whole bar into y dot y whole bar. Okay, so this is what I am going to get. After the simplification, we are going to get x plus y. So now we'll see how we are going to get from this input to this output. Here it is NAND gate 3. So these two are the input to this one. So now we'll see the realization of this NAND to OR. So what will be the output? What I am expecting, that is x plus y. Why? Because we are converting from NAND to OR. So x plus y is equal to x NAND x. So we know that this is one of the input for the first NAND gate and we are performing a NAND operation, and y NAND y is another input, that is from the NAND gate 2. So when it comes to the x NAND x, how we are going to represent x NAND x? If it is x NAND y, then we are going to represent it in the form of x dot y whole bar. In the same way, x NAND x, we have a NAND in the sense complement, that is x dot x whole bar. And if it is x dot x whole bar, based on the De Morgan's first law, what was the De Morgan's first law? That is x dot y whole bar, that is equal to x bar plus y bar. So this was the De Morgan's first law. So let me apply the same thing for this one. X dot x whole bar, that is also equal to x bar plus x bar, right? So 1 plus 1 is equal to what? 1. 0 plus 0, that is equal to what? 0. So that x bar plus x bar, that is also logically equal to x bar. So now understand one thing, x NAND x in the sense what? X bar. So let me do the same thing for this y. That is y NAND y whole bar. Why? Because we are using NAND gate. So if I apply the De Morgan's first law to this one, here also I am going to get y bar plus y bar. So at last it is also equal to y bar. So here y NAND y in the sense what? Y bar. So these are the two inputs now. Just understand, x NAND x is nothing but x bar and y NAND y is nothing but y bar. In between I have a NAND gate, right? Then how can I represent with an AND gate? X bar into y bar. So these are the two inputs and we are performing a NAND operation, that is product, and I have to recomplement it. Right? When it comes to the x bar dot y bar, let me apply the same to the De Morgan's first theorem. X dot y whole bar, that becomes what? X double bar plus y double bar. Why? Because here it has a 2 bars. So we have a complemented x input and it is recomplemented, that is equal to the original input itself. So that x dot y whole bar, then double bar we have. So when it converts from the De Morgan's first theorem, this becomes x double bar plus y double bar. So we know that x double bar is nothing but x, y double bar is nothing but y. Why? Because let me consider x is equal to 0. X is equal to what? 0. And I am going to have the x bar. X bar in the sense what? That is a complement of the x. So complement of the x in the sense it will become 1. Then I have a double bar. So double bar in the sense I am going to complement the complemented value so that 1 become again complemented. It will become what? 0. So then what it is equal to? Then it is equal to x itself. So in that way, when it comes to the double complement, that is also equal to the original value. So that x double bar is nothing but x, y double bar is nothing but y, or else it will get cancelled. Then we are going to have the x plus y. So x plus y in the sense what? That is OR gate. This is how we are going to get from the NAND gate to the OR gate. Getting? So this is how we are going to convert. So we are giving 2 NAND gate as an input and I am going to use the another NAND gate as an inverter. Then we are going to get an output as x dot y. So this is about the realization of all the basic gates by making use of the NAND gate. Now we'll see how we are going to realize NOR gate to all other basic gates. So we know that when it comes to the NOR gate, so what is the NOR gate? It will going to take 2 input x and y and that will be complemented, right? So OR will be complemented so that it become x plus y whole bar. From this one, we are going to get all the basic gates. So we'll see how we are going to do that one. So when it comes to the NOR to NOT, so NOR is nothing but x plus y whole bar. What I'm expecting then? I'm expecting x bar as my output, right? We'll see here, when it comes to the NOR gate, here purposely we are shortening the input of the value. Why? Because in NOT gate, in order to get a NOT gate, it has to take only one input and it will going to produce only one output signal. So that x will be the input. But you have to understand, it has 2 input, that is x and x. So when it reaches to the NOR gate, it will become what? X plus x whole bar. Why? Because NOR gate is nothing but x plus y whole bar. But here both the inputs are x value. So that x plus x whole bar. So x plus x whole bar. So now we'll see how we are going to do that realization. I'm expecting not x. That means inverted x that we are expecting. X NOR x. So how I am going to write? X NOR x whole bar. So this represents the NOR gate, right? X plus x whole bar. So based on the De Morgan's theorem, what was the De Morgan's second theorem? X plus y whole bar is equal to x bar into y bar, right? X bar into y bar. So this is about the De Morgan's second law. So let me apply the same thing to this equation. So instead of y, we have another x, that's it. X plus xy bar, that is also equal to x bar into x bar. Because my inputs are both x and I am going to get the output in the form of x itself, so that x bar into x bar. So we know that when we have a same input with a multiplication, then we are going to get a same output. That is, if it is 0 into 0, then the output will be 0. If it is 1 into 1, then the output will be 1. So in that way, x bar into x bar, that is also equal to x bar. So my input was NOR gate and my output is NOT gate. This is how NOR gate will be considered and NOR gate will be converted into NOT gate. That is x plus x whole bar, that is equal to x bar. So this is how we are going to convert from NOR to NOT. So now we'll see how we are going to convert from NOT to AND. So what will be the input then? Input will be x plus y whole bar. My output must be x dot y. We'll see how it will going to happen. Here I have a 2 NOR gate. So NOR gate 1, NOR gate 2. So these are the two inputs that I am giving. So here what I am doing, I am shortening the value of first input. So it becomes x and x. That means what? It will going to give us x plus x whole bar. Here we have another NOR gate, that is, it is taking y as an input. So y and y, this become y bar plus y bar. So these are the input. When it reaches to this one, what it will become? What was my first input? That is x bar plus x bar. So can I take it as x plus x whole bar? Yes. And we have one more input, that is y plus y whole bar. So this is one input, this is another input, and it will be whole complemented. Why? Because we are using a NOR operation. So it will be whole complemented. So at last I am supposed to get the x dot y as my output. Here it is x and y. Why it is x and y? That is nothing but we are looking for a x dot y. Right? So how I am going to do that? I have two NOR gate as an input. I am going to do the NOR operation. Why it complemented the input value, then we are going to get this x dot y. So we'll see now. I am seeking for x dot y is equal to x NOR and y NOR y. So why it is x NOR x? That is nothing but input of the first NOR gate. So here x and x are the two input. How can I write that x NOR x? That is x NOR in the sense addition, and I have one more input x. So it will be whole complemented. This is first input, and I have one more input, that is y NOR y, that is equal to y NOR in the sense addition. Another input is y, and it will be whole complemented. So it become y plus y whole bar. So I have to do the recomplementation. Why? Because NOR operation we are doing. So when it comes to the x plus x whole bar, I can write it as in the De Morgan's theorem, x dot x bar. So when it comes to the De Morgan's second theorem, that is x plus y whole bar, that is equal to x bar into y bar. So let me apply the same thing here. It will become x bar into x bar. When it become x bar into x bar, then that is equal to x bar itself. So it will going to apply for the same thing for the y input also. Then it becomes y bar. So now what are the two inputs? That is x bar NOR y bar. So these two are the inputs. F1 and F2 is nothing but the value of NOR gate 1 and NOR gate 2. So when it comes to the NOR gate 3, what I am going to do? I am going to take the input from first NOR gate. I am going to take the input from second NOR gate. Then I am going to integrate. What was the input of my first NOR gate? That is x bar, and my input of second NOR gate will be y bar. So x bar is first input, and I have a NOR operation here, NOR in the sense addition. I have one more input, that is y bar. So when it comes to the NOR gate, it will be whole complemented. So that is what they are saying, that F1 plus F2. So F1 is X bar and F2 is Y bar and we have a whole bar. So if I apply the De Morgan's second theorem, so that is NOR, what it become? It becomes X double bar and plus become product Y double bar. So this becomes what? So when it comes to the De Morgan's second theorem, we know that X plus Y whole bar is equal to X bar into Y bar. So if I apply the same thing here, first input is X bar plus Y bar, that will be whole complemented, that is equal to X double bar product Y double bar. So here bar will get cancelled and we are going to have a X dot Y as a output. So this is what I have explained here. So F1 into F2. So F1 in the sense what? X bar into F2 in the sense Y bar. So X bar in the sense F1. So that will be recomplemented. It become X double bar into Y double bar. So bars will get cancelled and at last we are end up with X dot Y. X dot Y in the sense what? That is AND gate. So now we'll see the output here. My input was X bar and Y bar, and when it comes to the NOR gate, X bar plus Y bar whole bar, that at last I got a X dot Y. This is how the realization of NOR to AND. So now we'll see how we are going to perform NOR to OR. This is similar to what? NAND to AND. So here what we are doing, we know the output of NOR gate. What was the output of NOR gate? That is X plus Y whole bar. So I am seeking for OR gate, that is X plus Y. So now we'll see how we are going to get this value here. Here I have a first NOR gate. So what is the input that I am giving? X and Y. So these two are the input that I am giving to the NOR gate. When I am using the NOR gate, this will become complemented, that is X plus Y whole bar. So I have one more NOR gate. So am I giving two inputs here? No. Instead of that, what I am giving? I am shortening the value of this output. So now you have to understand that for this one, when we are shortening the input into a single signal, at that time it will going to have the same input for both the values. That is X plus Y whole bar and I have one more input X plus Y whole bar. So it will going to reach us the NOR gate 2. So what is my input now? X or Y, that is what we are seeking for. X plus Y is equal to X NOR Y. Then what is this X indicates? That is X plus Y whole bar and NOR Y in the sense this X plus Y whole bar. So X plus Y whole bar, NOR in the sense addition, X plus Y whole bar. We have a NOR operation so that it will become complemented. So when it become complemented, here X plus Y whole bar. So that indicates X NOR Y. So in F1, the output will be X plus Y whole bar. So when it comes to the F2 is nothing but output of the second NOR gate. What was the input for that one? So there I have taken two input, that is F1. So F1 plus F1, we are using the NOR gate so that it will be complemented. So F1 plus F1, that is nothing but what? X plus Y whole bar double bar. So this is what the input. Okay, X plus Y whole bar. So let me consider this one. So this is what the representation of F2. So based on the De Morgan's second law, what I am going to do? X plus Y whole bar, that is equal to X bar into Y bar. So this is how I am going to convert. So F2 is nothing but what then? F1 bar into F1 bar. So this is equal to F1 bar into F1 bar. So 1 into 1 will be 1, 0 into 0 will be 0. So that in that way F2 become what? F1. So we know what is the value of this F1. So F1 is nothing but what? This value. F1 is nothing but this X plus Y whole bar. F1 value is x plus y whole bar, and I have bar here so that it will be recomplemented. So bar and bar will get cancelled. At last I am end up with this x plus y, and this will going to gives us OR gate. So what we are going to do, two inputs. So when I using this NOR gate, x plus y whole bar is my output. We are going to add F1 and F2 in order to get the F2. Based on the De Morgan's theorem, we are going to complement into F1 bar into F1 bar. So F1 is nothing but x plus y whole bar. Here when it recomplemented, it become x plus y double bar. Bar get cancelled. At last we are going to get x plus y, that will going to gives us OR gate. So we are at the end of this logic gate chapter. So when it comes to the logic gate, you have to concentrate on all the gates along with its truth table and logical symbol. After that, universal gates, there you have to understand the realization of the NAND and NOR with all the basic gates. I hope you all understood. Thank you very much. I am going to meet you in the next session. Until that, keep learning, keep on growing. Thank you.